Well, thank you, Lars, for introducing this program. My name is Kate Alexander. I'm an assistant professor at the University of Arizona, and I think we have a really exciting program for you here today. So my job is to just kind of set things up really quickly. I'm going to take just about 15 minutes to sort of go through kind of an overview of what you all are going to hear from later today. And then for the rest of the day, we have some really great speakers from all over who are going to delve in to a lot more detail about supermassive black holes and their destructive tidal forces, which is the cool title that got you all into the room. So hopefully my job is to explain a little bit more about what we're going to talk about, and then you'll hear in great detail from the rest of our presenters. So let's start real simple. Right, I have to turn this on before it works. Let's start real simple. So this is a view of the night sky, as you might see it if you were in a really, really dark location. Here is our Milky Way galaxy in the center here. And thank you, appreciate that. Here's our Milky Way galaxy in the center here. And of course, when people have looked up at the sky for millennia, they started wondering what this was. People had a lot of stories about what made up the Milky Way. When astronomers looked at the Milky Way more recently, the most obvious things we see are all of these stars. We see these dark dust lanes. But if you peer in towards the center of the Milky Way, you start to see some more interesting things. First, you see even more stars. This is a beautiful view from the Hubble Space Telescope. So this is many more stars than you could see with your naked eye, but you just sort of go in toward the center, you see more and more and more stars. And if you look in exactly the right location, right at the center, you can find these stars that are right at the very heart of our galaxy. And you can actually, take many pictures of these stars over many decades. And these stars are moving very quickly. So people took observations of these stars right at the heart of our galaxy over about 20 years. And you can see these stars right at the center are kind of whizzing around, completing a complete orbit in this 20-year period. And because we all know basic physics, we know Newton's laws, we know that even though we can't see what all these stars are orbiting, we can calculate how much mass it has. And if you work out what the massive object is, its location is marked by the little location of a star right here, we know that this massive object must have as much mass in it as about 4 million suns. So that's a really incredible amount of mass. It's crammed into a very small area of space here. There's only one thing we know of that can put that much mass into this small of a volume, and that is a black hole. So supermassive black holes, which will be the focus of much of what we're going to talk about today, are these black holes that are millions of times the mass of an individual star. We find them in a lot of places, and as physicists, particularly physicists and astrophysicists interested in some of the most extreme conditions available in our universe, it's really interesting to study them and learn more about them. So studying the black hole in our own Milky Way galaxy was an incredible feat. It won a Nobel Prize a few years ago for this incredible effort. But, of course, our Milky Way is only one galaxy. There are many, many galaxies out there. And in fact, astronomers think that every galaxy above a certain mass hosts a supermassive black hole at its heart. So what we'd really like to do is study not just the galaxy, the black hole in the center of our own Milky Way galaxy, but we'd like to be able to study all the black holes in all the other galaxies that are out there as well. Now, unfortunately, this is kind of hard. Probably the first thing everyone knows about black holes is that light cannot escape from them, right? And as astronomers, the primary way we use to study the universe is by studying light. So it might be, we might be kind of out of luck. In our own Milky Way, it's great because we're close enough to see individual stars orbiting the black hole, but we can't do that for more distant galaxies. So what do? Well, one thing we can do is we can look for hot glowing gas that's near a black hole. Now, when a black hole is eating gas, that gas heats up on the way in, so the gas hasn't fallen into the black hole yet, but we can still see light from that gas near the black hole. That's pretty cool. You can actually take a picture of a black hole. This is another incredible effort that was done by a very large international team fairly recently. They put a bunch of radio telescopes together all over the globe and effectively created one giant radio telescope the size of the Earth. If you do that, you can manage to take a picture of a black hole. You can see the little black hole in the center there. But this was really, again, quite difficult. So, when we're trying to tease out this light from black holes in the centers of other galaxies, tell it apart from stars, everything in the way, this is a very challenging effort. Fortunately, some black holes want to help us out. When black holes are consuming gas and when they're eating an awful lot of it, they're very messy in this process. So while most of the stuff manages to fall into the black hole, some of it gets spat back out in these jets of particles. And so black holes are actually some of the most powerful particle accelerators we know of in the universe. They can accelerate particles to nearly the speed of light in some cases. And obviously this process releases a lot of energy. And so if we're lucky enough to see one of these black holes that is really actively eating a lot of gas very quickly, we might see these powerful jets. And these powerful jets shine really brightly across the electromagnetic spectrum. They often show up really well in the radio part of the electromagnetic spectrum, but you can see them in X-rays, optical as well. And these jets are really interesting in their own right. They actually can grow large enough that they can shape the galaxies that the black hole is embedded within. So if you're interested as an astronomer in understanding how galaxies grow and evolve, when they form stars, when they stop forming stars, it can also be really interesting to study these jets from black holes. So this is really cool. Studying these jets from black holes has let us look out to very active black holes all the way back to the early universe. But unfortunately, most black holes are not in a phase of their lives where they're really actively eating a lot of gas. So we can see the really bright ones where there's a lot of gas nearby for them to gobble up. But most black holes are kind of more like the black hole in our Milky Way. Yeah, you had a question.
Yeah, so they burn.
Yeah.
But if the black hole is one way and the jet's the other, I'm trying to understand the picture of the jet going in both directions.
Yeah, so there's gas kind of coming in. It forms this sort of disk around the black hole, and it gets shot out along both poles. So you can think like the disk is kind of around the equator of the black hole, if you will, and then you get jets shot out around the North Pole and the South Pole. There's kind of this nice symmetry there. Thanks for the question. Yeah. Let's see. There's a question over here.
So my question is, these jets that are coming out, the holes, are they young? Are they old? I mean, where are they in their stage of life? Does every black hole have eat?
That's a great question. Yeah, so a jet like this one is probably pretty old because it took a while for material to get all that way far out from the galaxy. But we're going to spend a lot of time talking about today, which I'll introduce in a minute, are these tidal disruption events. And those tend to launch brand new jets, so we can see them right as they're being born. But jets are a pretty short-lived phase in black hole evolution. They can live maybe, 1 million years, 10 million years. Sounds like a long time, but these galaxies are billions of years old, so it's a very short phase in their evolution. Most of the time, they're not really doing much. In our own Milky Way galaxy, there's not a very powerful jet from our black hole. It's kind of more in a quiet sleeping state, if you will. So what I'm going to get to next is how we study black holes in this sleeping state where they spend most of their time. All right, one more question, and then I want to make sure that I have time to tell you about the other half of what we're going to talk about today, so I'll take more questions at the end.
Thank you. You said jets from the black holes, and they're gas jets. So a thought that occurred to me, are these gas jets, do they follow the classical fluid dynamics laws of motion?
Yeah, that's a great question. And yeah, they will follow these laws of motion. Some of them, because the particles are moving so fast, you have to make relativistic corrections. And so often what we're seeing is actually light produced, when this really fast-moving material is slamming into the gas and dust around it, you get shocks, and then you see light from the shocks as well. But yes, there will be, there's a lot of actually very exciting theoretical work going on in studying, exactly how these jets propagate, how they stay collimated as opposed to kind of spreading out. So yeah, but yes, they will all follow the basic laws of physics. All right, I love all these questions. I'm going to push on to a couple more slides, and then we'll have plenty more time for questions throughout the day. So okay, jets are cool, black holes are awesome, but most black holes are not actively producing jets, so we still want to study them. And so to study them, we're going to come back to this picture of stars orbiting a black hole. Now, as I mentioned, we can really only take this high-resolution picture where you can resolve individual stars in our own Milky Way galaxy. But looking at this, these stars orbiting around, you might have a question, which is, what happens if one of these stars ended up on an orbit that brought it really, really close to the black hole? So what would happen if one of these stars actually fell into the black hole and got eaten? And it turns out this doesn't happen as often as you might naively think, but it does happen often enough that we see it. And the nice thing is, when you throw a star at a black hole, suddenly there's a bunch of gas from that star right near the black hole. So even if the black hole has not been doing very much, if it's been kind of sleeping, it can briefly wake up, have a midnight snack, turn on, produce a new jet, produce some light, we can see it, and study it. And so this gives us a more unbiased way to study all the black holes that might be around in the local universe, even the ones that aren't actively eating a lot of gas. So this process by which a black hole eats a star is called a tidal disruption event, or a TDE. You're going to hear this term a lot throughout the rest of the day, so I wanted to make sure I got to it. So this little animation shows us what happens during a tidal disruption event. I've got my black hole down here, and here comes my unfortunate star getting close. As the star gets close to the black hole, it enters a stronger and stronger gravitational field, and tidal forces from the changing gravitational field become stronger than the star's self-gravity. The star gets torn apart and turns into this long stream of gas and debris. As that gas falls onto the black hole, it heats up and starts blowing, and you may also get this new little outflow or jet that is produced. And so basically what we're looking for is a galaxy where the center of that galaxy suddenly lights up, and then we go, aha, that black hole might be eating a star. We take other observations to confirm that, and then we can study that whole process. So here's a cartoon to kind of just go through this again. We saw the star coming in. It gets squeezed or disrupted. We call this spaghettification. This is a term that everybody loves. It is also the official technical term for this process. So a lot of that gas will end up falling onto the black hole. Some of it's actually gravitationally unbound from the black hole, so it just gets flung off into the ambient environment. We might hear a little bit more about this later today. Then that stream of stellar debris comes around and runs into itself. And it runs into itself, and when that process happens, you get shocks. That kind of helps the gas end up falling in toward the black hole. And then finally, all that gas falls onto the black hole. It heats up, and that's what leads to launching jets. So hopefully you already think TDEs are cool, but in case you don't, I just sort of briefly came up with 4 big reasons why we might want to study TDEs. One is we might want to, understand better how matter behaves in a strong gravitational field. You could even, test theories of gravity by comparing how we think matter should move really close to a black hole compared to how we see it. We can learn more about how black holes grow over time and affect their surroundings by studying this process of how they launch jets and outflows, and also how this accretion flow onto the black hole forms. We can use TDEs to study the galaxies they happen in, because there's some messy outflowing material from this process. You can learn more about the environment right around the black hole, which otherwise might be too far away for you to image directly if you don't have a telescope the size of the whole Earth. So we can learn interesting things about that. And then, as I mentioned, we can also sort of study the whole black hole population, not just the ones that happen to be particularly active at this point in time. And we can learn lots of interesting science by getting this census of all the black holes in our local universe, and also eventually black holes that are further away, and then we can learn how black holes grow and evolve over cosmic time. So in an individual galaxy, this doesn't happen that often. I should emphasize these are really rare. In our Milky Way galaxy, we expect a star to get tidally disrupted by our black hole about once every 10 to 100,000 years. But if you look at enough galaxies, you can start to see this happening all the time. And so we have these wonderful telescopes that just take pictures of the sky every night and look for anything that's changed and gotten brighter in the centers of galaxies. And we're now finding maybe 10 of these tidal disruption events every year, with telescopes like Palomar, which is not too far away, other telescopes around the globe. I'm a radio astronomer, so I have to throw up a radio telescope, which we also use to study TDEs, as you'll hear about this afternoon. And the reason we're having this conference now, the reason that some of us just spent 4 days talking about all the cool new science we're learning from TDEs, is we're really at a very exciting moment in this field. You know, a few tens of objects starts to be enough to do population studies of TDEs, but we're about to get deluged with an even larger flood of data. There are new telescopes being built right now that are about to become operational, like Rubin Observatory down in Chile. And this telescope is going to take deeper images of the sky than ever before. It's going to find a lot more of all kinds of transients, including these tidal disruption events. So soon we're going to have thousands of events to study, and we're going to be able to get a better view of black holes than ever before. So that's about all the time I have. So I'm going to turn it over to our excellent speakers. You should all have the schedule for today, so I won't go through this in a ton of detail, but we're going to basically start out with some physics related to black holes, then we'll talk a little bit more about how we make models of these tidal disruption events and understand what they mean. Then we'll break for lunch. We'll have a cool conceptual physics activity right after lunch, and then we'll get into observations of these tidal disruption events and what they can teach us about black holes in the afternoon. So I think I have time for maybe 1 or 2 more quick questions, but after that I'd like to turn the floor over to our first speaker, Eric. So anyone have any burning questions? Yeah.
I was thinking about as a star comes in and gets spaghettified, what tends to happen to its angular momentum? Does it tend to spin up the black hole?
This is a really great question, and actually this is one of the questions in the field that really confused people when we started studying it, because you get this star coming in on this really elliptical orbit, and we know somehow the gas ends up falling onto the black hole because we see it heat up, we see it produce X-rays, but we were trying to understand how do you dump all this angular momentum and form a little tiny circular accretion disk. And we think a lot of this happens in this like stream shocks. So you have this, you know, you initially form this like very elliptical flow, but then it runs into itself, and then a lot of energy is dissipated in these shocks, and it kind of comes down, forms a more circular thing. So we don't think that these TDEs really can play a big role in spinning up black holes, but this is also still a very active, ongoing area of research.
Thank you.
So yeah, excellent question.
Hi. Do we know yet, or are we at the point where we can start theorizing what happens to stars or planets in the path of the jet?
Ooh, that's also a great question. Yeah, you'd have to be pretty unlucky to be right in the path of the jet. It would probably not be very good for you. I think people actually have sort of looked to see if they could say anything, you know, about stuff that might be right along the path of the jet. I do remember one paper somebody like looked at that, but yeah, it's not super definitive yet. We kind of need better observations. I'll take one more quick question. I think you had your hand up here. Or if there's one more quick question, yeah. And then we'll switch to Eric's talk.
So have the TDEs been able to tell you how fast the black holes have been spinning?
Yeah, that's also a fantastic question. And that's one of the things we really hope they will be able to tell us. For a few, so there's a maximum mass above which you don't expect to see TDEs anymore, because for larger black holes, the event horizon is actually further away, so the star can get swallowed whole. But we've seen a few unexpectedly massive black holes that have produced TDEs. And so there we know the only way to do that is if the black hole's highly spinning. So for a few of them, we can say we found a few highly spinning black holes. But to figure out how to do that for the bulk of the TDE population, it's kind of a holy grail, if you will. And it's something we're working towards. Yeah, I think we'll probably have to move on, unfortunately. But we should have plenty more time for questions after the next talk. So I'm going to get out of the way and turn it over to Eric, who's going to start us off with some physics, and then which we all know and love. And then we will have time for, I think Eric has some plans to do interactions throughout, and we'll also have some time for questions at the end.